Hey guys, welcome back to CCL Biology, the channel for easy to understand biology lessons. If you are a high school student who needs some extra help with your general or AP biology class, or if you're a college student who needs some help with your introductory biology course, then this is the place for you. I am your friendly bio nerd. Thanks so much for tuning into my channel. In this video, I'm going to go over 5 great properties about water. So if you want a better understanding about the great things about water, then stay tuned. While you're here, don't forget to hit the like button below if you find this video to be helpful. And if you want more easy to understand biology lessons, then subscribe to my channel and hit the notification bell to get updates about new videos that go up every week. Okay, let's talk about water. It's everywhere. We drink it, we swim in it, we're made of it. But what makes water so great? It's great because it's perfectly suitable for life on Earth. Why? Well, water has 5 unique properties that we're going to look at. But first, I want to show you the structure of water, which is what allows it to have all those great properties in the first place. Okay, let's take a look at the structure of water. Water is a molecule, which is 2 or more atoms that are joined together by covalent bonds. Now, as you can see in this illustration here, a water molecule has 2 hydrogen atoms and 1 oxygen atom. And water is a neutral molecule, which means that its positive and negative electrical charges cancel each other out. But even though the charges cancel each other out, they still play a major role in the way that water behaves. The negative charge of this water molecule is gathered around that oxygen because the oxygen is holding the electrons within this molecule more tightly than the hydrogen atoms are. And the positive charge, as you can see, is centered around the 2 hydrogen atoms. Now, because the electrons are not being shared evenly across the molecule, water is a polar molecule. Polar just means there's an uneven distribution of electrical charge. So water is a neutral, polar, covalent molecule. And that polarity is just one reason that water is so suitable for life. Now, water is also unique because of hydrogen bonding. So let's take a look at that. Now, when water molecules are near each other, there's an attraction between the opposite charges. The negative oxygen region of one molecule is going to be attracted to the positive hydrogen region of another. Now, that attraction is going to bring the 2 molecules together in what is called a hydrogen bond. Hydrogen bonds do occur between other molecules as well. When we're looking at hydrogen bonds within liquid water, we have thousands, millions, perhaps even billions of hydrogen bonds that are constantly forming and breaking and reforming as those water molecules move around. Now, one hydrogen bond by itself is very weak, but a bunch of hydrogen bonds is going to make a body of water pretty strong. Hydrogen bonding is the other reason that water has such unique properties. So now that we've talked about water's polarity and its hydrogen bonding, let's look at those 5 properties of water that make it so great in no particular order. Number 1, cohesion and adhesion. What do these words mean? Well, to put it simply, cohesion is when something sticks to itself or bonds to itself, and adhesion is when something sticks to something else. Now, water does both. The hydrogen bonds between 2 water molecules keep them together, like we just talked about earlier. Now take that and multiply that one bond by 1,000,000. You get a bunch of water molecules that are attached to each other because they're attracted to each other. So this cohesive property makes water more organized than other liquids tend to be. And it allows water to form droplets and also to travel against gravity. This is what happens when water travels up the roots of a tree to get to the leaves, which is called transpiration. Each water molecule is going to pull the next one up with those hydrogen bonds in between them. So this is how water is able to travel up against gravity and get to every part of the tree. Now, the polarity of water makes it adhesive. It can bond to almost anything else that's polar. Now, this also helps with transpiration. So whereas the cohesive property of water allows those water molecules to stay attached to each other as the water travels up the plant, The adhesion comes into play because the walls of the plant, whether it's, a tree bark or whatever it is, are polar. And because water is polar, it's attracted to those walls of the plant. So that also helps it travel upward from the roots to the leaves. And another example of adhesion with water is, for instance, if you're drinking water through a straw. Now, water's cohesive property also gives it a higher surface tension than other liquids. Well, surface tension is basically how hard it is to break through the surface of a liquid. Now, all of those hydrogen bonds within a body of water creates what's almost like a net across the top of the water. And it takes a considerable bit of tension to break through that. So this is what allows certain objects to sit on top of water. And it also allows insects like the one you see here, this water strider, to walk on the surface of the water without breaking that surface. Number 2, high specific heat. Specific heat is the amount of heat that's required to change the temperature of 1 gram of any substance by 1 degree Celsius. So if we're trying to raise the temperature of 1 gram of a substance, then we need that substance to absorb a specific amount of heat. And if we want to lower the temperature of 1 gram of that substance, then we need it to lose a specific amount of heat. Now, looking at water, the specific heat of water is 1 calorie. That means that if 1 gram of water absorbs or loses 1 calorie of heat, its temperature is going to change by 1 degree Celsius. Now, this may not seem like a lot, but it's actually quite higher than most other liquids. There are a few exceptions, but for the most part, water has a high specific heat when compared to other liquids. Now, because water has a high specific heat, its temperature is not easily changed. It can maintain a relatively stable temperature over long periods of time. Now, why does this matter? Well, let's think about living things like us, which are mostly made of water. Now, we have dozens, if not hundreds, of chemical reactions occurring in our bodies all the time. And many of these reactions release large amounts of heat. I'm talking about heat that would incinerate us if it was, outside of our bodies. But the reason that we're not exploding from all of that internal heat is because the water that's inside of us is absorbing a lot of it. Now, as the water is absorbing it, the temperature of the water is fluctuating only mildly, so it's not a lot of movement in temperature there. So the specific heat of water allows living things, again, to maintain a relatively stable temperature. Now, this property also comes into play when we're looking at outside temperature. Cities or towns that are near large bodies of water, like oceans or bays or gulfs, generally have cooler temperatures than inland cities and towns. And that's because the bodies of water are absorbing the heat from the sun while staying pretty stable in temperature. Whereas on the other hand, as the sun is hitting the ground on those inland regions, that ground is heating up more quickly than the water is, even though it's exposed to the same amount of heat. Now, you can see the specific heat of water in action for yourself by taking 2 pots and put water in one and milk or some other liquid that's safe to boil at home in another. Make sure they have the same amount of liquid and the same amount of heat applied to them, and see which one boils first. Most likely it's not going to be the water, it's going to be whatever that other liquid is. Number 3, heat of vaporization. Now, this is actually related to specific heat that we just talked about. Now, when liquids become hot enough, when they're exposed to enough heat, then they're converted from the liquid phase to the gas phase, and this is called evaporation. Now, the heat of vaporization is the amount of heat that's required to convert 1 gram of a liquid into a gas. Now, remember, we said it takes a significant amount of heat to raise the temperature of water by just 1 degree Celsius. The hydrogen bonds within water give it a natural buffer to large temperature changes. So, of course, if we're trying to get the water hot enough to change it to a gas, we're going to need a lot of heat. So once that liquid water actually finally does begin to evaporate and change to water vapor, it's going to be releasing all of the heat that it had to absorb to get to that right temperature to begin evaporating. So that means that the water vapor molecules are really hot, meaning they have a lot of kinetic energy, they have a lot of movement. So as that water vapor is evaporating, then whatever the water is evaporating from, whatever surface it's leaving behind, is going to start to cool down. Now, why does this matter? Well, for us, it gives us a built-in cooling system, aka sweating. So when we sweat, water is evaporating from our bodies and turning into water vapor around us. Now that water vapor has the heat that was needed for the evaporation to begin taking place. And it's taking that heat away from our bodies and releasing it into whatever atmosphere we're in. So our bodies are the surface that the water is leaving from. So our bodies begin to cool down because the water vapor is taking that heat away. So this is the same concept for other animals and even plants. And on a larger scale, this high heat of vaporization helps the Earth as a whole maintain a relatively stable temperature. As water evaporates from oceans into the air, it takes heat with it. Meanwhile, the water that's left in the oceans will begin to cool down. Now, you can check out the heat of vaporization the next time you take a warm shower. Once you turn the water off and open the curtain or the door, and notice how quickly your body is going to cool down, even though the environment around you is going to be hot. That's because the water is leaving your body as water vapor and releasing that heat that was on your skin into the bathroom while you cool down. Number 4, less dense as a solid. Now first, let's talk about what density is. Density is defined as mass over volume. So I like to think of the definition as how much of something is in a certain space. So typically with density, we can use it to measure different things. Like for instance, hair density, like you see here, is a measure of how many strands of hair are in a particular area of somebody's scalp. So the more strands of hair that are within that area of scalp, the denser the person's hair is. And the fewer strands of hair in that same area, the less dense that person's hair is considered to be. We also use this for population density. So if we look at this picture here at the top, we would consider this a dense area because for this space, within this space, there's a large number of people. So that would be considered a dense area. So we use density in a lot of different aspects. Now, when we're looking at particles that exist in the 3 phases, solid, liquid, and gas, typically the most dense phase is going to be the solid form. So let's look at this picture and talk about why. So let's start with the gas. So here, when particles are in the gaseous state, the molecules are moving around a lot within their set space. There's a high amount of kinetic energy, which means a high amount of motion. So because those molecules are moving around so much in that space, there's a lot of space in between each molecule. So that's going to be the least dense, typically the least dense of the 3 phases, because there's a small number of molecules within that space as compared to the other phases. So as we move to the liquid phase of that, looking at that same particle, the molecules start to slow down. There's less kinetic energy, so there's not as much movement. They're still moving, but not as freely as they would have been if they were still in the gaseous state. So the molecules start to get closer together as they're moving less and less within that same space. So because we're getting more molecules within that same space, the liquid phase is typically more dense than the gaseous phase. Now, as we move to the solid phase, here there's little to no kinetic energy. These molecules are going to be stable for the most part. They're not going to be moving around too much. There's typically an order, as you can see here in this illustration. So because there's pretty much little movement, we're going to typically have as many molecules as we can within that same space. So because of that, typically the solid phase of a substance is going to be the most dense. So as we go from gas to liquid to solid, density usually increases. Now, water doesn't follow those rules. And the reason that it doesn't is because of the hydrogen bonds that we've been talking about. So here we see an illustration of 5 water molecules with the hydrogen bonds that are between them. Now notice how much space there is with these hydrogen bonds. And that's because the water molecules are trying to stay kind of as far apart as they can while still being attracted to each other. So you see, for instance, here, we have this positive hydrogen atom that's attracted to this oxygen atom. So they're still trying to have some degree of space, although they're attracted to each other. And what we don't want is one hydrogen atom being close to another hydrogen atom. Since these are both positively charged, they're repelling each other. So that means that water molecules have to have a certain degree of space in between them, even though they're attracted to each other. So when we look at water in this shape, this is actually called a tetrahedron shape. It's like a cool triangle pyramid type thing. So that comes into play with the density of water. All right, so let's start here with this warm water picture. Now here, the oxygen atoms are being represented by the red circles, and the hydrogen atoms are represented by the smaller blue circles. All right, so here in this picture, you can see that the oxygen atoms are kind of oriented towards the hydrogen. So you see like the red and blue there, the red and blue. So kind of the same thing as the last picture I was showing you. So again, we see this space here, and that's space to allow the hydrogen bonds that are in between the molecules. Now, of course, the hydrogen bonds aren't pictured here, but you can just imagine them in between these spaces. So here, this water is still in the liquid state, which means that these molecules are moving around. So because they're moving around, there's still a good degree of space in between them. So this is not highly dense. Okay, now let's see what happens as the temperature decreases. So as the water gets colder, the kinetic energy is going to decrease, which means there's less movement between the water molecules. So let's look here at this circle. So here we see that the water molecules are coming closer together. Now we still have to leave space for those hydrogen bonds. But remember, when water is in the liquid state, the hydrogen bonds are forming and breaking and forming and breaking. So that kind of allows the water molecules to get a little closer together because the bonds keep forming and breaking. So because we have more molecules within the same space, cold water is going to be more dense than warm water. Now, as the temperature goes down even further and then the water begins to freeze, here we get to the ice state. Now, if water behaved like most other substances, then we would expect the ice or the solid state to be the most dense, right? But clearly we see here that's not the case. So again, remember, with other substances, as we move from the liquid to the solid state, those molecules would pack in tightly and form this organized, non-moving structure. But that's not the case with water. Now, the molecules are barely moving. There's very low kinetic energy, so that's the same as with other solids. But the difference is, now that they're staying in place, they need that maximum amount of space between the hydrogen bonds. So here the bonds are represented by these dotted green lines. Okay, so we see that organized structure here. So because we have to have such a large amount of space for those hydrogen bonds, we're not going to get a lot of water molecules within the same space. As we can see, between the ice, the warm water, and the cold water, the ice has the least amount of molecules within the same space. So that's going to make the ice the least dense. Okay, so that's why solid water or ice is less dense than liquid water, because there are fewer water molecules within a given amount of space. Okay, I'll say that part again. Solid water, aka ice, is less dense than liquid water because there are fewer molecules within a given amount of space. Remember, density is how much of something is within a certain space. Okay, so we also see that represented here. So with the liquid water, again, the oxygen is red and the hydrogens are gray. We see kind of a disorganized illustration here because the water molecules are still moving around some. So we're able to get them pretty close together. All right, but when we get to the ice part of it, once again, we see kind of a more organized structure with a lot of space in between for those hydrogen bonds. So we have fewer molecules here on the ice side than we do on the liquid water side, which makes the ice less dense. So this allows water to float, or should I say this allows ice to float when it's in liquid water. Now, why is that important for us? I mean, floating ice is cool, but what does that have to do with our biological survival? Well, for one thing, this is important for marine creatures. Because ice is less dense than water, that means that when we have bodies of water like lakes, rivers, or streams, it's going to freeze from the top down because the ice floats. So rather than freezing from the bottom up, which it would do if ice was more dense than liquid water, it freezes from the top down because the ice floats up to the top of the body of water and then it begins to freeze. So this is helpful because it gives the body, it takes a long time for that body of water to completely freeze over all the way down to the bottom. If it froze from the bottom up, then the fish and the other animals living in the water would die. They would freeze pretty quickly. But again, since it's freezing from the top down, it takes a much longer time for an entire body of water to completely freeze over. So that's pretty helpful for the animals. And number 5, a universal solvent. Now, let's take a look at some vocabulary first before we go further. Now, a solution is made of a solute and a solvent. The solute is whatever is being dissolved. So for instance, salt or sugar. The solvent is whatever is doing the dissolving. It's like water or oil, typically some type of liquid. So when you put those together, you get a solution. Now, water is typically known as a universal solvent. And that's because of something that we like to say in biology, which is like dissolves like. So that is in reference to polarity. So polar substances tend to dissolve other polar substances, while nonpolar substances will dissolve other nonpolar substances. And of course, polar substances will not dissolve nonpolar substances and vice versa. So like dissolves like. Now, because water is polar, it can dissolve pretty much anything else that's polar, like salt or like sugar. So if we look at this illustration here, you see a spoon of salt about to be poured into a glass of water. So if we were to zoom in on that, once that polar salt hits that polar water, the salt is going to break apart or dissociate. So here we see salt, which is sodium chloride, NaCl. So you see Na+, those are the positive sodium ions. And then the Cl negative is the negative chloride ions. So it's breaking apart in that water. Now remember, water is made of hydrogen, which is positively charged, and oxygen. So the hydrogen, which is positively charged, is going to grab hold of these negative chloride ions, while the oxygen is going to bind to the positive sodium ions. So that's essentially how water is going to dissolve the salt, because it's bonding itself to the salt so that eventually you're not able to separate the salt from the water. Now let's take a look at what happens when we try to put a nonpolar substance like oil with the polar substance like water. So if we look in this illustration here, as the oil is being poured, it kind of looks like it's going to start to dissolve or mix with the water, but what happens is they actually begin to repel each other. Now, of course, the oil can't jump back out of the cup as much as it would probably like to, but when we say repel each other, in this instance, they're going to stay separate. Okay, there's not going to be any mixing, any dissolving, or anything like that. So in this case, of course, oil is less dense. So the oil forms a layer at the top, but as you can see, they're completely separate because one is polar and one is nonpolar. Well, that's it for today's video. I hope it was helpful for you. If so, then please leave a thumbs up in the comment section below. And if you have any remaining questions, then type those in the comments and I will do my best to provide you with an answer. Thanks again so much for watching CCL Biology, that is Christ-Centered Life Biology. God bless and bye-bye.